Okay, so welcome everybody. Thanks for joining, and thanks a lot to Don Towsley for being with us. He prepared a very nice keynote talk titled "The Quantum Internet: Recent Advances and Challenges," and we have today 1 hour for discussion with Don. Before starting, let me just read the bio of Don. I'm sure all of you know Don, but nevertheless, let me read his bio. Don Towsley holds a Bachelor in Physics and a PhD in Computer Science from University of Texas. He is currently a distinguished professor at the University of Massachusetts in the College of Information and Computer Sciences. He has held visiting positions at numerous universities and research labs. His research interests include network science, performance evaluation, and quantum networking. He was co-founder and co-editor-in-chief of the ACM Transactions on Modeling and Performance Evaluation of Computing Systems, and has served as editor-in-chief of the IEEE ACM Transaction on Networking and on numerous editorial boards. He has served as program or co-program chair of several conferences, including Infocom 2009. He is a corresponding member of the Brazilian Academy of Sciences and has received several achievement awards, including the 2007 IEEE Koji Kobayashi Award and the 2011 Infocom Achievement Award. He has received numerous Test of Time awards and also the 1998 IEEE Communication Society William Bennett Best Paper Award. Last, he has been elected fellow of both the ACM and IEEE. So again, Don, thanks a lot for being with us, for accepting to prepare this keynote for NetComNet. Very interesting, a very challenging topic. And since I'm speaking, let me take the privilege of starting with the first question. But while I do that, let me repeat what I said before. So attendees wishing to ask questions should write a message on the chat so that we can use the chat as an ordering mechanism in order to have a token passing protocol for questions. So if you want to ask a question, write your message on the chat. And to begin with, my question is, how long do you expect it will be necessary for some of these quantum internet technologies to become a reality? Can we imagine they will be coming during the next decade? Quantum computing has been slow to emerge, and we know of the big difficulties that are there for the technology. And going to networking seems much more of a challenge. So is this going to become real in a reasonable time frame?
Well, I guess the question is, what is reasonable time frame? I would say that certainly in 5 years, there will be small experimental networks. I think probably the first setting where it'll become a reality will be, I'll say, a data center, a quantum data center, where you have a bunch of small, noisy quantum computers, and then you'll have a switch, let's say, that will allow them to connect to each other. That I would imagine will occur, in the 5 to 10 year frame. And after that, it's really tough to predict. As you know, the technology, it's really challenging, and the technology, although it's progressing, it progresses slowly.
First request for questions from the chat, which is Michele Segata.
Go ahead, Michele.
Yeah, thank you very much. First of all, thank you for the talk. It was very exciting to listen to. And actually, I have quite a lot of questions. So let's say I will continue until somebody else asks for the token, and then I stop and I'm going to ask the token again. The first questions are more on the practical side. So how you realize these things and on some principles of quantum networking. So you have been saying that you might have the chance that the transmission of your entangled photons might not be successful. But if it's successful, how long does the entanglement last? So can Alice and Bob keep their photons entangled for, let's say, a lifetime, or is there a lifespan in which they...
Right. So there are a number of different technologies for quantum memory. And first of all, let me preface to say that I'm not an expert on that. The kinds of memories that you would probably put in switches have short lifetime, but it's possible to build memories that you can have, let's say, in the computers themselves, that you know, could last seconds, maybe even minutes. So it is the sort of, to me, that's a long memory lifetime, but clearly when you generate them, you're generating them to consume them pretty soon.
Okay. And regarding their consumption, how do they synchronize their measurements? So you distribute your entangled photons, and then let's say Alice does the measurement. How does Bob knows that Alice did the measurement? Can they synchronize, or do you need another channel to do the synchronization?
I think that what you would have, you need a control plane. It's going to be classical, and that's how that kind of synchronization is going to take place. You know, and so you could imagine as you're generating entanglements, you also have like a classical header that sort of indicates, let's say, a sequence number kind of thing, and then Alice says, I measured, and this is the outcome, and here's the bits that you need to make a correction, so that we're stay okay.
I will leave the floor to Alberto and then come back again if there's time. Thank you for the time being.
Sure, and I'll say that to me, although we haven't looked at it, it's really interesting how you're going to combine the classical and the quantum. I think that'll be a really nice research topic.
Thank you.
Hi, Don.
Hello, Alberto.
Yeah, so from the little I know about this technology, I understand it's very noisy. That's one of the main issues. So my question to you, instead of reducing the noise, maybe there are several applications of the fact that we have a noise environment, like in security, encryption. So is there research in this area about applicabilities of noise to use it for? To
use the noise?
Yes.
That's interesting. Certainly, of course, that's done in classical. No, I'm not aware of work going on that's trying to take advantage of, let's say, noise in a quantum setting. You know, the concern really is how to deal with it and compensate for it.
So, Michele, you can go on again. There is nobody in line.
All right.
Thank you.
Let me just remind people, if you want to ask questions, please write so in the chat.
So yeah, this question actually comes from me and Renato as well, which we were already discussing about this morning. And it's how do you actually implement a quantum switch? Does it need to be a quantum computer, or is it a smaller device or easier to make device?
So first of all, it doesn't exist yet, except in very, very, very experimental fashion. There seem to be two architectures. One is what I really talked about, that the network is trying to generate and distribute, let's say, end-to-end entanglement. As I understand it, the technology required at the switches are not what you need for a full quantum computer. And for that reason, that looks like it should be doable over the next, let's say, within 5 years. The second architecture is one that looks more like a classical network, and that is you transfer quantum information across the network. And there, in order to do that, you need huge amounts of quantum error correction. And so that's going to require much more sophisticated switches and routers that are going to start to look much more like a complete quantum computer.
Great, thanks. So leaving again to Edmundo, but I'm always in list.
Can I go on?
Yes, Edmundo, go ahead, please.
I don't know if it makes sense, the question, but since the technology is very expensive, I imagine that you have a core in some part with the quantum computer in several years from now, but you have to have a mixture of regular internet and the quantum computer. How do you foresee this kind of architecture? Is really one core in one place and then connect to the current internet? Or can you say something about it?
So I think that what is going to happen is that, okay, well, we're going to start off with very small area quantum networks. But really, as they build out, I think that they're going to essentially follow, let's say, the topology of a classical network, except that you may need to have quantum repeaters, let's say, sort of spaced at regular intervals across, let's say, a 100 or 200 kilometer length. You might put 2 or 3 that'll just be used for quantum. I think there is a question right now. I expect that the quantum part is going to be a different hardware than the classical part, but there's a lot of work on, how you can take an optical network and really share the wavelengths between quantum and classical, and eventually that's what it's going to look like.
Okay, Michele, floor is yours again. You are monopolizing the station. Okay.
It's so interesting. I could go on for hours, but I don't want to bother Don too much. Another question I had was more on the research side. So in your keynote, you were talking about communication based on optical fibers to transfer photons. But I've seen that already in 2012, some scientists managed to transfer them using a laser, so through air. And I was wondering whether you think it might already make sense to start thinking about mobile wireless quantum networks and their applications, of course, or is it something that might never see the light?
Okay, this isn't what you were sort of looking for. I've been working with a colleague with NASA and sort of to come up with an architecture for a mobile satellite network. And the sense I have is that some of the issues that we will deal with there are issues that would apply, let's say, in a terrestrial setting, except that up in space, you don't have to deal with noise. And so you can go much longer distances. The problem with free space is going to be really that noise is going to sort of limit the length of the links, whereas with optical you can go much farther. But people are thinking of it. One problem is, of course, that many components have to be refrigerated. I shouldn't say many, some. And so I think there's work on trying to figure out how warm you can make things. It's interesting. When I first started off, people would talk about room temperature quantum, and by that they mean 4 degrees Kelvin. And refrigerating is when it's millikelvin in their minds.
If I can jump in without using the chat, if refrigerating remains at these levels, isn't there the risk that all of this goes the direction that superconduction went, right? So 30 years, 40 years now that superconducting materials are there, but their use is limited just to high money science and little else. Do you think there is the risk for, in general, quantum computing and quantum communications to go in the same direction? So remain something that will not reach the broad population?
That's a good question. I don't really know the answer. I know that a lot of what experimentalists are trying to do is to really raise the temperature to a point where the hardware cost, although it may still be several $1,000s, it's not hundreds of thousands of dollars, and that maybe it could even go down to hundreds of dollars. Even that, of course, would be probably too expensive for it to be just completely universal. But I think it suffice for at least having a backbone network, and with certainly some organizations being able to connect directly to it. Others would have to perhaps access it through some sort of a portal.
John, what is the toolbox that is necessary in order to tackle the analysis of quantum communication, quantum networking? Can we work with our standard tools, or we need much more or something very different?
So I have a student who used sort of continuous time Markov chains to develop a model for quantum switch. And actually this work appeared in Sigmetrics, maybe it was last week. And basically, we distill the physical behavior into sort of assumptions that made it very easy to write down the model. The challenge is, so I think that we can use many of our tools. The challenge is understanding the quantum system well enough to really be able to make the right assumptions. And I have to say, all the papers I've written so far has included at least one quantum colleague. I think I'm getting to the point where my group and I can probably write papers relying just on our knowledge of quantum. But I think it's really important, from the start to work with somebody who, is well versed in quantum. But our tools apply.
Okay. Edmundo.
It's really a follow-up question. So with Marco asked about the tools that we have, but do you think is there any chance to have to revise protocols for data transmission for a quantum network? That's something I still don't quite understand. Do they have to be all revised because of the communication, or can we import some of the knowledge we have with protocols to that area?
I think there's really a lot that we will be able to borrow. In, let's say, a network that's generating entanglement, you have to worry about path selection. path selection. That probably means you have to worry about the quality of links. And so, okay, you define some measure of link quality, and then maybe you use something like a Dijkstra style algorithm for essentially coming up with a good path. Having said that, I think there are also opportunities where you maybe be able to go beyond using classical techniques and take advantage of that it's quantum. I think there's going to be a huge amount of room, of course, for cross-layer optimization, as much or maybe even more than in the wireless domain. I shouldn't say more, it's probably equivalent. I think it's easy for people to think that somehow it needs a completely brand new way of thinking of protocols, and that's not the case. There was something that I left out of the talk, which because of time, you know, there's this notion, property of the no cloning theorem, that you can't make copies of qubits. And so, of course, when we do multicast or broadcast, that's all about making copies and sending them around. And so you might think, well, I guess there's nothing that we learned about multicast is useful here. But it turns out that there's a way to take the ideas from multicast and use it to come up with sort of new protocols for generating and distributing entanglement to different users, and that don't violate the no cloning theorem. So, you know, it's again, and what I found interesting is the physicists had never thought of it. And that's an example of where, you know, somebody working in classical networking can take ideas and apply them to quantum.
And, can I ask one more quick question?
Absolutely.
Yeah.
Of course.
And let's say measurements, taking real measurements, not the ones that with quantum, but to understand the network that's been embedded in the internet since the early ARPANET. I don't have any idea of how can you infer, let's say, the state of the network in this environment. Is that a wrong thinking, or be possible?
So I think it's possible, and I've been talking to a physicist who he developed, I guess, the area of quantum tomography, which is to try to understand and characterize a quantum system, either in terms of the quality of the quantum state that comes out given inputs, or even the functionality. And so we've been talking about taking ideas from classical network tomography and combining it with his. I think even minimally, you can just use ideas from classical network tomography directly, because, you know, Alice and Bob are generating end-to-end pairs. They know the rate at which they're trying to establish them. They see the rate at which they succeed, so they can sort of measure an end-to-end, let's say, loss probability. You could have lots of Alice and Bob pairs doing this, and so then you might be able to take ideas from classical network tomography that could then allow you to combine these measurements maybe into a linear system, and then solve it to try to get a sense of what's going on at individual switches or individual links. So I think that's going to be a really interesting research area.
It's very nice. Thanks.
Pasquale?
So we have a request for a question by Pasquale Ventrella.
Yes, I'm
Please
here.
go ahead.
Okay. Good evening to good afternoon to everyone.
Hello, Pasquale.
You mentioned earlier that it could be interesting combining quantum and classical communications. How do you think the last one could be helpful, and which existing technologies do you think can get along with quantum communications?
So at this point, I see quantum communications as solely concerned with transferring quantum information or quantum state or generating quantum entanglement at, let's say, end-to-end nodes. But, you know, you need addressing. If you have, let's say, a router or a switch, you need to be able to route and switch. And I see all of that taking place in the classical world. And so I'm guessing that eventually somebody will define, I'll call it a quantum frame standard, or a frame standard for a quantum network. It's going to include quantum information, and it's going to have, let's say, a classical header and maybe a classical trailer. And they will be sent at the same time, either on completely different networks or in the same optical network, but at different, on different channels.
Okay.
A long-term research problem area might be, is there a way to do some of the control in the quantum plane? I have no idea, but you know, it may be that somebody in 10 years will figure out that you can do some of it, and that'll be pretty cool.
Okay, thank you.
So back to Michele.
Well, actually, the other questions I had were already been answered. Two other questions. So yeah, I had a question on other applications rather than security and cryptography, but you already replied to that. And the other one was on the, let's say, generation rate of the quantum bits, but you also were replying to that. So
So one thing I'll mention, of course, I guess everybody who's been asking questions, except for Edmundo, are from Europe. I'm sure you're aware of this European initiative that started in 2017, maybe it was 2018, €1 billion initiative on quantum. And so there's really a strong quantum networking thrust that's part of it, that is being led out of Delft. And I'm sure it includes people, of course, at other universities, but certainly, you know, if you have interest in this or learning more, that would be a group to sort of reach out to. They could also tell you who's participating in Italy and Germany and so on and so forth.
Yeah, the problem is that this whole area is attracting a lot of curiosity, but the threshold that you have to pass in order to be able to do something meaningful seems fairly high. So whenever I try to approach this field, I start reading things, and then I feel really discouraged. I mean, it seems like you need to invest a lot in order to be able to start discussing and making something meaningful.
I have to, I agree with that, and I have to admit, I was fortunate. I have a colleague, as I said, who's been on every paper that I've been involved in. I met him through a classical networking project, and he got involved because there wasn't enough money in quantum. And as we sort of worked together, he just kept telling me about all of the exciting opportunities in quantum networking. And we would meet maybe once a month to talk about it, and we'd start to like try to formulate problems. And then at the next meeting, I couldn't remember anything about quantum behavior. And he had to spend the first half of the meeting explaining it. And it went on and on like that until, you know, finally, all of a sudden, it was staying with me. And, you know, maybe the thing to do is, of course, is to enter it through students. Have them take the quantum mechanics class, and so that they really understand the quantum. And then, but where they're really interested in communications and networking, and to learn the quantum, but just instill on them, you know, the way to do research, and, you know, from networking perspective, what are important issues, what are not, and train them.
You should convince your friend to write a Quantum 101 for networking. We promise 1 million citations. We will learn it by heart.
You know, I have talked about that. You know, I guess at this point there are a number of sort of papers or monograms on what does a networking person need to know about wireless. And I'd love for us to produce the equivalent. You know, what does a networking person need to know about quantum? So
that would be fantastic.
Yeah.
Because it's not easy, even to navigate the technical literature. You don't know what you have to know. So initially, my feeling is that the barrier is quite high. Surely too high for me.
Yeah. Michael, I have to say, I wish I were 20 years younger.
We all do.
I'm really sorry that I'm entering into this area as a senior researcher.
We have a question from Anna Aguiar.
Hello.
Yes.
Unfortunately, I cannot turn on my camera because I still didn't configure the permissions. I will do that after this question. And I hope this is not the last question, because I don't think it's a good last question. But I have been trying to look into quantum computing stuff with a colleague and a student, of course. And I have a lot of trouble, and it's good to hear that you also have this thing of what the hell every time. I'm still feeling, I have this feeling I really don't dominate this. But there's one thing that I realized, they are computer scientists, and they sort of abstract everything. So this is on quantum computing. They abstract everything, and then we work from our abstractions, which is what you were describing right now. But my question is more related to this this jump to the physical things that will. I'm an engineer, so there will have to be a device, and isn't quantum too sensitive to, or very sensitive to temperature? And do you think that is masterable? So I'm asking you to look into the future, of course. Temperature seems to me something that makes me sort of uncomfortable on the physical side.
Right. At this point, it seems to me that like a quantum switch is going to have refrigeration for some components. I think what I hear is that maybe I can get by with just cooling down photon detectors. That might suffice. And for that reason, it's going to be orders of magnitude more expensive than classical components. You know, that's not to say that in 20 years it'll be down in price such that people could have something at home, but at this point I don't see that. And so I think you're going to see sort of small networks initially. As I said, it could be a data center. You know, Google has several small computers and is capable of building more. Likewise with IBM, likewise with Microsoft. And I can imagine at some point they'll want to network them. And then eventually I think that'll grow out to sort of metropolitan area networks, and then finally wide area networks.
Renato, it's your go.
So I don't know if this is a good last question, but let's try. You were talking about a broadcast or a multicast quantum communications. And I was wondering if, and you said there are techniques from our traditional methods that can be exported there, but can this be in a network, or they always request intervention of the source to avoid?
Okay, so let me start with, so the physicists have proposed the following sort of approach for generating entanglement among 3 or more parties. You have this network that generates Bell states, and then what they do is they augment the switches with some additional circuitry that can be used to essentially combine Bell states in a way that you know, if you want something for 10 parties, eventually it's a 10-party entanglement. Another approach, and this is, I was surprised that they hadn't thought of it, is, well, first of all, I said, well, suppose that you have the second architecture where you transfer quantum information. What would you do then? And what they said was, well, we would generate this complicated state at a source, and then we would transmit each qubit to the intended receivers or intended nodes. Okay, well, so that looks like naive multicast, right? You make copies of the packet and you send it. So what you can do then, you can emulate multicast in the sense that you just generate a Bell state, you send the qubit down a tree to the other nodes, and when you get to a bifurcation point, then you perform a little bit of logic on it and start expanding the state, and then send those qubits down the appropriate segments of the tree, and just repeat the process. So we're not doing multicast, but we're using the basic idea behind multicast there to essentially distribute entanglement in a more efficient way. And, you know, as I said, it's not something that the physicists who were worrying about this had ever thought of.
And you were saying you would use some of the state to do this. So you...
Right. What you're doing is you're always distributing a qubit that's part of the state down the tree. And whenever you have branches coming out of a node, you run some quantum logic on that qubit and expand the state, and then send it down the different branches.
Thank you very much.
So let me thank very much, Don. This was extremely interesting. It's really something.
Thank you. I mean, this was fun. As I said, it's an exciting area, and it's really great to be able to try to get some excitement across.
I was really excited when we started discussing this conference. I asked Edmundo for one thing, which was convince Don to give a keynote speech on quantum networking, and Edmundo promised me, and we made it, and I'm really happy because this is something which I believe is important for our community. Being able to move to these new territories which are largely uncharted for our community, I think it's extremely important, and I think you are doing great work on this, and I hope you will really write that paper on what networking scientists have to know about quantum to do something useful, and I'll read it. I'll be the first to read it.
Okay. And yeah, if anybody has further questions, just email me.
Okay, thanks very much, Don. You've been extremely kind and extremely supportive. So, thank you. Just a round of virtual applause.